Hello, this is Erick DeWolf at Kansas State University, and I'm thankful for the opportunity to be part of this plenary session and share some of my ongoing research. Let me begin by sharing my screen and we'll be underway. So this is an opportunity for me to share some of the work that I and some of my colleagues have been doing here in the United States on trying to use predictive models to guide strategies or develop strategies for in-season scouting and pathogen surveillance. Let me begin with a little historical context. So if we focus on striped rust here and look at our historic estimates of disease losses here in Kansas from 1976 to 2019, we can see that striped rust was relatively a non-issue until around 2000, 2001, when some new types of striped rust, new races of striped rust that were virulent on some of our widely used sources of genetic resistance and were better adapted for life here in the warmer wheat production regions of the central United States were introduced into our region. Since this time, we've had these episodes of severe disease or striped rust epidemics relatively frequently in Kansas, and the disease has quickly become the #1 wheat disease within our state and within our region. So within that context, we want to look at some of the conventional wisdom here of wheat rust epidemiology in this region, in the Central Great Plains region of the United States. And what I am showing you here within this map of the United States is the areas of wheat production, which are shown in these shaded regions here in the central and south central regions of the United States. The colors on the map, or the intensity of the colors, represents not only the density of wheat production, but also the frequency of wheat production, with the orange and up to purple and blue areas showing the most frequent and intense areas of wheat cultivation. So the conventional wisdom for rust epidemiology in this wheat producing area is that the rust diseases typically do not survive in these central regions, but rather survive in the south central portion of the United States, primarily within the state of Texas, as I'm indicating here by that initial dashed red line. The growing conditions and the environment within this area that favors the overwintering can also set the stage for potential movement through the extent of that overwinter survival, but also the local conditions influence the ultimate size of that pathogen population within these potential source regions. The timing or the size of that pathogen population then influences or sets the stage for potential movement north on storm systems and ultimately into the central portion of the United States, into Kansas, where I'm located, but also additionally further north into other key wheat producing areas of the United States. The timing of these migrations relative to wheat growth and development influences the amount of yield loss. And of course, the local weather conditions also govern the number of secondary cycles and ultimately the amount of disease severity, disease intensity of these disease epidemics. So it's within this context of striped rust being a recent arrival here in the United States with around 20 years of experience, in addition to this conventional wisdom of the epidemiology of rust diseases in this area, that we look at some potential goals and also potential challenges nested within this research study. So our goals are twofold. One is we'd like to be able to do what we call scouting. So we're going to, by scouting, I mean we're taking these observations of disease intensity and using these observations to support in-season management decisions, namely the application of fungicides. Now, the wheat yields and economic situation of wheat production in this region of the United States and often is such that growers would prefer not to use a fungicide in many years just to try and maintain the profit margins of their wheat. We also have a additional goal as plant pathologists within this region of pathogen surveillance. And by pathogen surveillance, I'm referring to efforts to monitor the pathogen population for changes in virulence, in effort to support the wheat breeders in their effort to try and better control these diseases through genetic resistance. Any information we can provide these wheat breeders on sources of resistance that appear to be showing weaknesses to the current pathogen population helps them inform their own crossing and breeding processes. Now, the challenges are that if you consider the conventional wisdom of the epidemiology, is that these putative source regions are very large geographical regions. If we look at Texas alone, it's some 670,000 square kilometers. And certainly a systematic survey of all these different wheat producing areas would be exhaustive. In terms of resources for personnel and then also financial resources to support this massive effort. This is also a considerable distance from some of the wheat production areas where I'm located in Kansas, representing some 700 to 1,000 kilometers of distance from these potential source regions. Which increases the complexity of surveys that we might do. We might only be able to make 1 or 2 trips into this particular area, or we would need to work with colleagues already located in Texas. But even that said, they would greatly appreciate or benefit from strategies that would help them refine where and when they look for these different diseases. So let me put this in terms of different research questions. Are there particular areas of Texas that play a critical role within the development of these striped rust epidemics within this area? Are there also time periods that are particularly influential in the development of these epidemics? And ultimately, can we use this information to inform our pathogen monitoring efforts and our efforts to manage the striped rust within our region? So let me give you a brief overview of some of our modeling approach here. Here, we're going to use some of those historical observations of epidemics, whether it's a major disease year, a low disease year. We're going to code that ultimate yield loss here in Kansas as a binary variable. We're going to pair those observations of disease with different summaries of environment, whether it's temperature or rainfall, or some particular measures of soil moisture that were originally developed to quantify soil moisture for agriculture purposes. Because it's a binary response variable, we're going to use non-parametric measures of association or correlation, in addition to logistic regression selection procedures to try and identify potentially important source regions and time periods that are related to the disease development within this overall Great Plains region. So let me get right to some of the key results here. We found that soil moisture was probably better indicators of some of the disease epidemics than either temperature or rainfall. In this case, the Palmer Z index, which is part of an overall Palmer drought severity index that's widely used in the United States, was strongly associated with striped rust outbreaks in Kansas. Now, if we focus specifically on regions of Texas that are defined by the National Weather Service, known as climate reporting districts or climate districts that are shown in these particular maps, there are 2 primary time periods that rise to the top as being influential. One of these is occurring in November, and particularly influential, as shown here, is that there's a stronger relationship shown in these dark blue colors in north central and extending down into the south central, with a slight shift towards the eastern portion of this region. By February, that association weakens in the northern portions of Texas and largely contracts to the February time period in that central southeast portion of Texas. Now, these 2 time periods correspond roughly to when the winter wheat is being established in the southern Great Plains. So planting conditions followed by rapid periods of hopefully growth and establishment of that crop, and potentially the fall establishment of rust within this area. The February time period is going to correspond to post-winter conditions where the pathogen population may have contracted back to some of these south central areas, but also is more time to a period where the pathogen may be undergoing different secondary cycles, production of inoculum, build above that population, and setting the stage for potential movements north on different storm systems. So the challenge here is how can we use that model, these model results to try and inform our strategies? And the other challenge is not only to apply this information to ours, but is there a conceptual framework that would be applicable for your region of the country, your region of the world? It may have a very different epidemiology, and I would encourage you to look at both your current understanding, but also investigate the possibility of looking at using predictive models to help inform your strategies. So here's a brief summary of what I would propose as strategies for monitoring rust diseases in the central United States. So clearly one thing that we would want to do is use these modeling results to direct at least some of our resources to these putative epidemiologically important regions. This would include potential visits to this kind of north central eastern portion of the wheat producing area. Even though this isn't necessarily the most intense area of wheat production in the state, it appears that there's a considerable empirical evidence that these are epidemiologically important. We might also revisit these locations following the overwintering, in this case, focusing our survey efforts further south to see how the pathogen has potentially overwintered and what the source regions and potential pathogen diversity is in the February time period. Now, with that said, I think it's also wise to work with colleagues within Texas to try and always maintain some base level of monitoring within other large areas of wheat production. So this might include some of the other north central, northwestern areas of Texas to try and enrich our survey samples from that. But I think it also gives us some key leads on very early indicators for disease development that may be occurring 3 to 6 months prior to the actual outbreak of disease and timing for disease management further north in Kansas. So some of the key takeaway messages is that in a general sense, the models that we've been developing are helping to refine our own understanding of the wheat rust epidemiology in the Great Plains. These models are also helping us develop strategies for pathogen monitoring, and particularly helping us identify these epidemiological key regions within the state of Texas and within our region, and also key time periods. So again, I would close with just the call for you to think a little more deeply. How could these same or similar type of conceptual frameworks be applied to your area, and to better use the available resources for pathogen monitoring activities, whether it's intended to support in-season management decisions or to simple surveillance of these pathogen populations within your region. So with that, I'll acknowledge some colleagues, graduate students, and funding for all of this work. And I look forward to seeing you in the question and answer period following the plenary sessions. Thanks for your time and attention.